Howdy, howdy, this is Mr. Potter. In today's lesson, we're going to be taking the area under the curve that we've been talking about for the past two lessons, and we're going to be talking about how to extrapolate that into the concept of volume. And we're going to be doing this over several days, and so the first day we're going to be talking about strictly volumes that are determined by their cross-section. So I want to talk about what that means. So if I'm looking at this as volume, I really want to start off with some x and y axis and some function that we're used to. Let's say something like y equals radical x, which I'm going to be evaluating but from x equals 0 to x equals 5. And let's also say for our purposes that I want to look at cross-sections that are semicircles. In other words, if I were to look at this situation, I'm actually looking at a cross-section that looks like a semicircle. So let me go ahead and draw this out here so you can see what I'm talking about. And of course down here at x equals 0, my cross-sections, my semicircles, are actually, the radius is very small because the radius is determined by the y-coordinate. But as I get farther out on the x-axis, the radius of each of these cross-sections gets much bigger. And so what I could do is I could add all of these little cross-sections and say that my volume is approximately equal to the sum of these areas for each cross-section, as my cross-sections go from 1 to k cross-sections. And as we so often do in calculus, we want to see what happens as I let these things get smaller and smaller. Now I'm looking at the area of the cross-section, but keep in mind that volume is supposed to be three-dimensional. This area here is only two-dimensional, so I need to multiply it times this third dimension, which is delta x. So I'm really multiplying the area of each cross-section times delta x to get a volume of a cross-section. And then each of these cross-sections I'm going to be adding together. So as we often do in calculus, we want to know what happens as the number of cross-sections tends towards infinity. In other words, when I'm looking at this, remember that as the number goes to infinity, this delta x really becomes dx, and the summation really becomes an integral. And so what I'm doing is I'm integrating the cross-section area times dx, but this cross-sectional area is actually dependent on the x value, and x is going to range from 0 to 5. So what really happens here when I look at this as an infinite sum, I'm still looking at the exact same graph that we just looked at, the graph y equals radical x from x equals 0 to x equals 5. But my cross-sections end up becoming super thin because delta x is approaching 0. I actually end up with dx. And what I have to do is I have to come up with some type of formula for this cross-section, some type of formula for area that depends on x. And of course this formula is going to be determined by the shape. So in this particular example, I want to know what's happening as this area ends up being a semicircle. And what we'll talk about today is we'll actually go through this through several different shapes, and we'll really get a workout from our geometry. Really have to remember a lot of those formulas that we had from back in geometry. But what I'm really doing here is I'm going to be coming up with a formula for a semicircle, which I know is 1/2 pi r squared, but I'm not interested in r. I really want this to be a function of x. And so this ends up being 1/2 pi times my radius, the distance from the center to a point on the curve, namely the y graph, which is radical x, that I'm going to be squaring, because that's r. So what I've got here is I've got a function, a as a function of x. And so what I want to do with this is I want to determine the volume, and I know that my volume is supposed to be the integral from 0 to 5 of my area function times dx. which ends up being the integral from 0 to 5 of 1/2 pi times radical x squared dx. This is actually not a bad integral to have here. First off, I've got this constant 1/2 in pi that I can pull completely out. And I'm doing the integral from 0 to 5 of, well, radical x squared is just x. And so if I integrate x dx, I end up with my constant pi over 2 times 1/2 x squared, which I'm evaluating from x equals 0 to x equals 5. And so what I end up with is I end up with 25 pi over 4 by evaluating that integral. So I've got a nice volume here, this volume that actually extends out this way and this way, whose cross sections are going to be these semicircles. And you're not going to be expected to draw these things three-dimensionally, but it certainly would help if you could kind of visualize what's going on. Actually take a look at what my cross-section looks like. And if you can't draw it three-dimensionally, just draw a semicircle. But realize that this point here is actually the point on the graph y equals radical x. So in this case, my radius ends up being radical x. So I want to go through a few examples of dealing with these shapes, determining the volumes, where the cross sections are different geometric figures. So I want to start with, let's say that I'm still going to be dealing with the graph y equals radical x from 0 to 5, but this time I'm going to say that the cross sections are squares. So I'm looking at this graph. Here's my graph y equals radical x, and I'm doing this from 0 to 5, and each of my cross sections are supposed to be squares. So that's what each cross section would look like. And I know that when I'm dealing with a square, I know a formula for the area of the square. The area of the square is supposed to be the side squared. But remember that this height here is actually my graph y equals radical x. So that means that this side is radical x, and because it's a square, this side up here must be radical x. So my formula for area as a function of x has to be radical x squared, or just x. And so what I'm going to be doing is to find my volume. My volume is equal to the integral of my area function times dx from my starting endpoint to my ending endpoint. So this ends up being the integral from 0 to 5 of x dx. And so this ends up being x squared over 2, which I'm evaluating from x equals 0 to x equals 5, or 25 halves. So what I've got here is I've got a whole bunch of square cross sections. And so my figure is actually doing something like this. Okay, again, I'm not going to expect you to draw it, and I certainly am not very good at drawing these figures either. But I do expect you to be able to come up with this cross-section down here and to relate it in terms of the function that we're dealing with. Remember, our function is radical x for all of these examples. And we're going to be dealing with this from 0 to 5, so our limits aren't going to be changing. The only thing that will be changing is this area function, area as a function of x, which I'm going to have to figure out in order to perform this definite integral. So let's do another example. Let's say I want to do the same thing. I want to do the function y equals radical x on the domain from 0 to 5, but my cross sections are equilateral triangles. So if my cross sections are equilateral triangles, what I've got here is I need to take a look at what I've got. I've got my graph y equals radical x, and again I'm evaluating this from x equals 0 to x equals 5. But each one of these cross sections is going to be an equilateral triangle. So I'm going to need to remember some behavior of the area of an equilateral triangle. And the first thing I know is that for an equilateral triangle, all my sides are the same, and all of my angles are supposed to be 60-degree angles, pi over 3 radians. What I know is I know that my height is determining by this function. My height is radical x. But I also know that this divides this into a 30, 60, 90 triangle, and I remember those relationships from my geometry class. I know that if this is my long leg of a 30, 60, 90 triangle, my short leg ends up being the long leg divided by the square root of 3. And so my base ends up being 2 times radical x over radical 3. And I know the formula for the area of a triangle is 1/2 base times height, so this is going to be 1/2 my base, 2 times radical x over radical 3 times radical x. So what I've ended up, when I do some simplifying here, my area function as a function of x ends up being x squared over radical 3. So this is the function that I'm going to be integrating. I'm going to have to be integrating this function. My volume is equal to the integral of my area function as a function of x times dx, from x equals my lower end point to my upper end point. So this ends up being the integral from 0 to 5 of x squared over radical 3 dx. Excuse me, did I say x squared equals 3? Ooh. That should be just x over 3. My bad. I am so sorry. So this is what I need to integrate. And I've got radical 3 in the denominator. That's a constant that I can pull completely outside of my integrand. So I've got 1 over radical 3 times the integral from 0 to 5 of x dx. And so I end up with x squared over 2 times this 1 over radical 3. And I'm evaluating this from x equals 0 to x equals 5. So this is going to give me 25 over 2 radical 3. And so that means that when I'm taking a look at each of these cross sections that are equilateral triangles, and I'm taking a look at the volume that's generated, I end up with this wedge type shape. But the volume of this ends up being 25 over 2 radical 3. I want to do one more example of this. Actually, I want to do 2 more examples. The first one I want to do is I'm dealing with y equals radical x on the same domain, 0 to 5. And I'm going to tell you that my area is a rectangle that's 3 times as wide as tall. In other words, my rectangle is going to be whatever my height is, my width is going to be 3 times that height. So again, I'm dealing with the exact same graph, y equals radical x from 0 to 5. And when I take a look at these cross sections, however tall this height is, my width is going to have to be 3 times as much. So I end up with these really wide rectangles. And so if this height is determined to be radical x, then this width is going to have to be 3 radical x. And I know that my area is supposed to be length times width, but that ends up being 3 radical x times radical x, or 3x. So what I'm going to be doing to determine my volume is equal to the integral of my area function, dx, from my lower bound to my upper bound. So this ends up being the integral from 0 to 5 of 3x dx. And 3 is a constant, so I can pull that completely out of my integrand. I've got the integral from 0 to 5 of x dx, and this is x squared over 2 times the constant I pulled out, which I'm evaluating from x equals 0 to x equals 5, which is going to give me 25 over 2 times 3. And one of the things I hope that you're noticing is that this 25 over 2 keeps popping up. The only thing that's really changing for these is my scale factor. When I'm dealing with area, area is a two-dimensional aspect, and so I should end up with something squared. And the only thing that's going to be different is the constant, whether I'm dealing with pi or whether I'm dealing with a radical 3 in the denominator, or in this case, because my rectangle's 3 times as wide as it is tall, I end up with a 3 in front of it. But that's determined, these rectangles that have this width that's 3 times as much as the height. And of course, this is what my shape would look like. It's not going to be a beautiful drawing. It's not going to be a perfect drawing, but you get an idea of what's going on here. What's important is being able to see this cross section. So I want to do one last example. The thing is, we keep talking about these cross sections. These cross sections really could be any shape. So if I'm dealing with y equals radical x on the same domain from 0 to 5, but my cross section is a circle, then what I've got is this. I've got my graph y equals radical x. But now when I draw my cross section is going to be a circle. So normally when I think of a circle, I think of a circle in terms of its radius, pi r squared. But here my diameter is the distance from the bottom of the graph to the top of the graph, and this whole diameter is radical x, and so my radius ends up being 1/2 radical x. So my area function as a function of x ends up being pi times my radius squared, or pi over 4 times x. And so to determine this volume, my volume is the definite integral of my area function in terms of x times dx from my lower bound to my upper bound, which ends up being the integral from 0 to 5 of pi over 4 times x dx. And pi over 4 is a wonderful constant to take completely outside of my integrand. And when I integrate x, I end up with x squared over 2, something that's very familiar to what we've been doing so far in these examples, which I'm evaluating from x equals 0 to x equals 5. So I end up with pi over 4 times my 25 over 2, which is really 25 pi over 8. Again, what's important to notice here is for what we've been doing, one, we have to figure out this area of our cross section. And we do have to get it in terms of x. We really need a formula that involves solely x. Not r, not base, not height, not perimeter, not any of those other constructs, but just our independent variable. And notice that because we've been using the same function and the same domain, the same integral value keeps popping up, just times some scalar value. In our previous example, when our cross-section was a rectangle, there's that 25 over 2 with a scalar value of 3. When we did the example of a triangle, here's that 25 over 2, just with that scalar value of 1 over radical 3. And when we did the example of a square, we end up with 25 over 2 with a scalar value of 1. We're just not writing it. So, the important part of this lesson is being able to find the cross-section formula. They're going to be the formulas that we've learned from geometry. A formula for the area of a square or a rectangle or a triangle or a circle or some other closed figure. And then we're going to have to incorporate that into the formula that we came up today, where our volume is equal to the definite integral of the area times dx on some closed domain, some lower bound to some upper bound. So once again, this is Mr. Potter. Thank you for watching. Have a great day.